All right, your hand gets cold when you touch ice. That one's going to be wet. Exo. All right, exo. Now, to explain this, how would you go about doing so? Yes.
The heat is leaving your hand in going from your hand into the surroundings. Hence, since there's less heat energy on or in your hand, it is getting colder.
Yeah, so you're losing heat to the ice, releasing heat, losing heat, all goes under the exothermic banner, okay? So keywords here, releasing and absorbing. For releasing for exo, absorbing for endo. Okay, so heat transfers from the warmer object to the colder object, the one that's releasing heat. That is going to be exothermic process. The one that absorbs heat is going to be endothermic process. So the opposite is true here with the ice gets warmer when you touch it. Now the ice is the system. That means the ice is acting as the, no, it's the system, but so is that ice endo or exo then in this situation?
Endo.
It's going to be,
absorbing the heat.
it's absorbing the heat from the surroundings, therefore that would be endothermic. Now the next couple, shifting over into phase change here. So water boils in a kettle being heated on a stove.
Endo, because the water while it's boiling is going from a liquid to a gas. We know that requires breaking IMF.
All right, lock it up, people. Up here, let's go. All right, yes, water boiling. You can sleep right there. Means that, and it also gives you a context clue here. It says it's being heated, which means you're putting energy into the system there, you're heating it. But if it's boiling, it means it is going from a liquid to a gas, so that heat is being used to overcome the IMFs holding the particles together. So, overcoming IMFs means like breaking forces, means you need to put in energy, means that energy has to be absorbed. All right, so now we're on to D. Water vapor condenses on a cold pipe.
Exo, because it's going from a gas to a liquid, it says condensation.
Yes, gas to a liquid. Now, when we're talking about the heat being released, remember gas particles are have a lot of kinetic energy and are moving very fast. They must slow down, and you must form some IMFs for them to transform back into the liquid. And in doing so, forming is warming, forming IMFs. But slowing down particles, that means energy is being released to the surroundings. Ice cream melts. Endothermic, we're melting now. We're overcoming forces to change it from a solid to a liquid. Okay? And doing so, adding in that energy overcomes forces. The particles have a little bit more free movement, and now we'll have more kinetic energy once they're all shifted over into liquid phase. And you have to give it heat. You have to, it has to absorb heat to overcome those forces. All right, this is a good one. So each of the following will define a system and its surroundings and give the direction of the energy transfer. Methane is burning in a Bunsen burner in the laboratory. What is our system?
Methane is our system. The surroundings is the laboratory. It is exothermic because when you burn something, you feel the heat coming towards you because it is releasing heat from the system.
Correct. Methane is one part of the system. Does anybody can identify the second part of the system here? Methane alone by itself cannot burn. No, it's not the burner. The burner is in the surroundings as stated before. That is true. System is made up only of the chemicals involved. So, what's the other chemical involved here?
Oxygen, because combustion requires oxygen.
Now the oxygen is being given to the system from the air. Do remember air is a homogeneous mixture of a bunch of different gases. 78% nitrogen, it's about 19-20% oxygen, and then a bunch of trace gases, CO2, argon, a bunch of stuff. So the other part of our system is going to be oxygen from the air. And yes, the correct statement before is true that when you're burning something, we, the observer, the person observing, we are in the surroundings. We are from the surroundings perspective, as would be the thermometer or the temperature probe. So to us, it's going to feel warm. So when the bonds are breaking and forming, we feel the warmth. This is exothermic. That means heat is going from the burning of the methane to the surroundings, from the system to the surroundings. Okay? So here, burner and the lab, these guys are going to be your surroundings. Okay? And this is going to be exothermic. So it's going to go from the system to the surroundings. Now, that one was a chemical reaction one, so make sure that you're keeping that kind of in a separate bucket from the phase changes. Because in chemical reactions, you have bonds breaking and bonds forming. You have both going on at once. But whichever one is the net higher is going to be the one that determines the overall reaction. In this case, obviously, the amount of energy in the bonds that were being broken is greater than that in the bonds that are formed, so that energy is released to the surroundings. B, though, is more of a phase change idea. So out of here, what is our system? Water drops are our system. Very good. Oops. System, and the surroundings, skin, air, pool, all that, wherever you are swimming, those are going to be the surroundings. And in this process, we have evaporation. Evaporation means liquid to gas, okay? This process right here, as you can see. So, what is actually happening here, transferring from the what to the what?
Transferring from the heat to the skin to the water drops is endothermic, and we know this because in order to go from a liquid to a gas, we need to break IMX, which is kinetic energy.
So, from the skin into the water, this is endothermic, it's absorbing it, it's overcoming the forces, holding the liquid together to turn it into a gas. And this is actually also the same idea, same rationale as to why sweating actually cools you off. Some people think it's just because you're wet. No, it's not really because you're wet. Your body generates the water so that as the heat of your bodies increase, the water is absorbing the heat from your skin, and then it eventually evaporates off. Okay, so that's where that process is actually taking energy away from your skin and cooling you down. All right. Now, this is a nice conceptual one too, and I give you kind of a diagram here to help you, but you really should be looking for the context clues here. Hydrogen gas and oxygen gas react violently to form water. Explain. Which is lower in energy, a mixture of hydrogen and oxygen gases or water? Context clue that's going to tell you whether this is exo or endo. What's the context clue?
It's that they're forming, they prefer to form water as opposed to oxygen and hydrogen. And we know that when they form, it's to lower their energy level. Since they're lowering their energy level, that means the energy has to be released. Exothermic.
This is actually right here being represented as water vapor, gas form here. So let's stick to what we know here. What signals this in the problem to telling you whether it's endo or exo? There's a key context clue that should be, rings a bell. Reacts, things could react either way. The violently part is the key word here, violently. Okay. Violent means kaboom. explosive, vigorously, okay? Now, because it goes boom, violently, we know combustion always going to give off heat. That's just based in the nature. It's going to burn, explode, whatever. So in this case, then, this is going to be exothermic. All right, so if it's exothermic, then we have to think about which one is higher, reactants or products in terms of the energy, the potential energy in the bonds. All right, so you can easily, draw yourself an energy profile diagram like so. If energy is being released, we know which line is lower than the other.
Product is going to be lower than the reactant.
It's going to look something like this, right? The products will be lower than the reactants. Very good. So, because the delta H here in between, delta H is going to have to be negative. So, then in that case, that should give you plenty of idea as to which is lower in energy. Is it the hydrogen and oxygen or the water vapor? The water vapor, good. Because this amount gets released to the surroundings since it's exothermic. And we can see if it's exothermic, the bonds that are formed in the products have to have less energy than the bonds that were broken in the reactants. That energy goes somewhere, it leaves the system, goes to the surroundings, exothermic. All right. Okay, so I just put this in here not because you really need to utilize this for any kind of problems or anything, but some of math savvy people like to know where these equations are derived from. So the change in enthalpy, or delta H, also known as heat of reaction, at constant pressure the change in enthalpy is the heat gained or lost by the system. It is derived from a series of equations. One of them is work equals the negative pressure times the change in volume. And that is the compression or expansion of a gas. There is a device that they use to measure this. And then they measure all these things for different reactions. They come up with their values and they stick them in tables that are in the back of your textbook in the appendix. So that's one of the equations, is the work equation. And I told you earlier that work was going to eventually get factored out as you derive these equations and put them together and substitute. So the internal energy equation that we already looked at, this is the heat plus the work, okay? Now there is another equation in the textbook showing you that the heat of reaction is equal to the internal energy plus the pressure times the change in volume, okay? So if you substitute in, okay, take this part out and you substitute in the work part, which you can shift over the negative sign. Then you can insert the negative W in for the P delta V. And as you'll notice, you have positive W, negative W, they cancel out. So really, delta H is measured to being the heat at constant pressure. So, once again, like I said, you won't be expected to do anything with this, but like I said, from a theory standpoint, some people like to know where it comes from. This is the device. They have this bulb flask. They input their stuff. They have attached to a piston container to where it has the ability to move the volume and change the volume as the reaction progresses. So this is how they're actually measuring the work. Not really important, but like I said, just want to show you, like, I'm not making this stuff out of thin air. There's actual theory behind it. So, what do we know about change in enthalpy? We need to know that it's a state function. State function means that we care about the initial state of our reactants and we care about the final state of our products, and we look for the difference between them. Now, we don't really care about the pathway. Pathway goes in a different section, okay? Final minus initial, not the middle or the path. So for example, if we all wanted to like go to a Centerville Chantilly game at Chantilly High School, and we all met up here at Centerville High School and we're going to drive over there. And, you know, we all left at the same time, but that doesn't mean we're all taking the same roads to get there. You might know a different way than I would go. You go up 28, you go up Stringfellow. There's lots of different ways to travel from Centerville to Chantilly High School. Difference is, our starting point is Centerville High School, our ending point is Chantilly High School. That's our initial and final states. The in-between, the roads you took to get there, doesn't really matter. However, I would point out certain roads, certain pathways are going to be faster than others. And that's the piece, the pathway part goes under kinetics because that's talking about the speed of the reaction. So we will address that part later on when we get to kinetics. So far, most of the stuff you're going to see in this section and in a couple other units are going to be state function, and you'll see them because they're change of, they're final minus initial, and you have the delta in front kind of symbol. So delta H, final minus initial at constant pressure. And an easier way to represent it when you say H products minus H reactants. Okay, that's what you see on your potential energy diagrams. Product line minus a reactant line, and you can figure out delta H there. All right, so change in enthalpy, delta H, products minus reactants. What you'll notice here though, burning of methane, we kind of talked about this. Burning of methane with oxygen produces carbon dioxide and water. Now, highly exothermic, negative 890 kilojoules. That's per mole of reaction that burns. So lots of energy being given off. But going from carbon dioxide and water to the methane and the oxygen reactants, that would be, if we were able to reverse it, the magnitude will still be 890. The difference is you would have to input that kind of energy into it, which is a high threshold of energy. The magnitude would be the same to go the opposite direction. You would just change the sign. That's important for later. Now, delta H, like I said, just write down, is also called heat of reaction, and you'll see it written a lot like this. Delta H, R, X, N, like so. There are a bunch of different types of delta H's depending on which particular reaction you're talking about. Like they have the heat of combustion, they have the heat of formation, they have heat of solution. They have a bunch of different ones that they narrow down to specific types of bond breaking, bond forming, or forces forming, forces of being overcome type deal. But once again here, this example of the hydrogen plus oxygen gives you water vapor. You can see on the energy profile over here, this graph, the enthalpy change, that the reactants are at a much higher energy than the product. So that means this amount where the arrow is pointing, going down, that is going to be released to the surroundings. So delta H is less than 0, going to be negative. And exothermic, because delta H, when it releases energy, is negative, showing the sign that it's leaving the system. All right, couple of things about enthalpy. Enthalpy is extensive. So extensive versus intensive. Everybody remember those properties? You can define them that way. Physical properties. Extensive physical properties means it's amount dependent. So the amount of reactant that you put in there will generate a certain amount of heat. And if you add more reactant, then you get more heat and so forth. So I like the analogy of like a campfire, wood burning fireplace. If you burn a log versus a twig, which one's going to give you more heat? Log. That's more amount of material that you're burning. Okay? Delta H for a reaction in the forward direction is equal in size but opposite in sign for the delta H of the reverse reaction. Now, the methane example, using it as an example, saying, yeah, the reverse side of that doesn't actually usually take place in nature. That one's not usually a reversible reaction. But we can still mathematically manipulate things using that principle that if you were going the other direction, you would just change the sign on it. Magnitude's the same for the forward and reverse, but the signs are opposite of one another. Delta H for a reaction depends on the state of the products and the state of the reactants. Now, when we say state, we're talking about physical state, phase of matter. Like gases of their nature have a lot more kinetic energy than liquids or solids. So in order to take something that is a solid, react it with something to turn it into a gaseous product, that's going to take more energy than starting off with gaseous reactants to make gaseous product. It's already in those phases, and they're already having a lot more energy to begin with. So phase of matter, and you'll notice on the tables too that they have the different delta H's for different phases of matter because of that. All right, so now we're going to take a look at the basic of delta H problems here, where you're trying to figure out how much heat is absorbed or released using a chemical reaction. I call this enthalpy stoich. It is the basic of the basics. So they gave us the delta H for the reaction, and they're telling us that we're inputting 5 grams of propane. I'm assuming then, because they told us only about one reactant, that the oxygen, of course, oxygen and air is pretty much an excess amount that you can utilize when you're burning stuff. Now, the thing that you need to know about the delta H here is this is really kilojoules per mole of reaction. So, what does that mean per mole of reaction? That means every time the reaction runs one time, you generate 2,221 kilojoules of heat that goes from the system to the surroundings because it's exothermic, delta H is negative here. So, but per mole of reaction means you need 1 mole of propane, you need 5 moles of oxygen. That means you're going to produce 3 moles of carbon dioxide and 4 moles of the water. So you use the mole ratio of the balanced equation here for this type of problem. So you just start off with your 5 grams of propane, C3H8, okay? And now in order to use the mole ratio, we obviously need to do what with our grams? We need to convert it to moles. So I'm going to diagonal down grams to 1 mole of propane. Now you can go ahead and add it up, but your molar mass is going to be 44.11. 3 carbons at 12.01, 8 hydrogens, 1.01. There we go. Now, this is the part you're going to take your mole of your propane, diagonal that down here. Mole of the propane. And we know 1 mole of propane right here generates 2,221 kilojoules of heat. Now you can leave the negative sign in here. The negative sign really though is just telling you it's being released. Okay, so when you calculate this, the grams cancel with the grams, moles cancel with the moles, and then we're left with our kilojoules, which is what we want because we want to know how much heat is being released, generated when we burn that much propane. And propane, oh, by the way, is in your gas grill tanks. So you know this is something typically that people burn. So 5 times the 2221 divided by the molar mass here.
Like 251.
Well, 252 because we start with 3 significant figures over here. So So I'm going to keep 3 in my final answer. So 252 kilojoules released.
I'm serious.
You could write it that way, stating that it's being released, or you could put negative 252 kilojoules. Either way, your answer would be acceptable. All right. And we are correct. Now, the last one in this section, we're going to be talking about burning the oxygen instead. We're going to assume we have endless amounts of propane and we're going to use 5 grams of oxygen. How much would that produce? The only slight difference here, you set it up the exact same way. The molar mass of oxygen obviously is different. That's 32 grams per 1 mole. But every time this reaction runs, how many moles of oxygen do you use? 5. So this would be 5 moles O2 to the 2221 kilojoules. Like I said, you can put the negative in or leave it out or put released at the end. But in this case, you'll notice we're going to get a lot less heat if we only use 5 grams of oxygen.
For your answer, do you need to put the negative sign of release?
Yes, you would want to state whether it's, and I'm getting 69.4 kilojoules released. Or yes, you could put negative 69.4 kilojoules.
Wait, what do we put for the first one?
Either one would be fine.
Yeah, but do you say release for the first one? No,
Yes, because they're both, this is exothermic. I know it's exothermic because our delta H up here is negative. So the heat is being released. And it also says right here in our problem, heat released. So we also know it's exothermic.
Okay. Yay, no more.